Welcome to Watkins Waggle, what a good one looks like. And we're talking about methods. So we're talking about rates of reaction, how fast a reaction happens, and we're talking about the different ways in which you could measure that rate or calculate that rate, or how we'd write a method using correct apparatus to do that. This PowerPoint's been emailed to you, but obviously I'm going to show you the slides here and talk you through what you should notice on those slides and how we can apply it to exam questions. On this slide here, you can see there's a range of different ways in which you can measure a rate of reaction. We'll start off with looking at a reaction that produces a gas. First thing is really, how would I know that that reaction produces a gas? Almost all questions about a chemical reaction will give you a balanced symbol equation. Those symbol equations involve state symbols. We're looking at state symbols and why they're such a big clue for you in a different video. For now, let's just focus on the fact that this reaction does release a gas. So it requires us to use a very specific piece of apparatus, the gas syringe. It's just like a syringe that you might have used in lessons, a little plastic one, but this one is made out of glass. Okay, it's a large syringe and it starts fully closed. As the reaction that's happening in the left-hand bottle, the conical flask, produces a gas, the syringe moves outwards and there are measurements down the side, just like a measuring cylinder, that allows you to measure it. The key point is that a gas syringe is much more accurate than using a measuring cylinder. The other point to note is that the first gas that's going to be forced into the gas syringe will always be air. There's always going to be some air in the conical flask and in the delivery tube. That's the tube that connects the conical flask to the gas syringe. It delivers the gas, therefore it's called a delivery tube. If you do get air into the gas syringe, then assuming that you've set up the experiment in the same way every time, you'll always end up with roughly the same volume of air in that gas syringe every time. So that would be a systematic error. You're going to end up with that same error. So the overall pattern of your results won't be affected. So it won't affect the outcome of your experiment. So that's a gas syringe, and that's how we'd use it. We could also use a different type of method. We could use looking at a gas being released. We could always look at the actual mass of the liquid that we've got. So in this experiment, we've got a balance. Now, if you do food technology or catering, you've called it a weighing scales. It's not in science though, we call it a balance. Get the names of the equipment correct, okay? Not a weighing scales, it's a balance. Get the names correct, you get extra credit for using the correct specialist vocabulary. You'll notice at the top, it points out there's a cotton wool plug. Okay, so literally a lump of cotton wool stuck in the top of this conical flask. Why is it there? Well, we want the gas to escape, so cotton wool will allow the gas to escape, but also this reaction could be fizzing and bubbling. That means it might spit, and you don't want the liquid to escape because that's going to affect the mass of our experiment. And the only thing that we want to affect the mass is the gas leaving. How quickly the gas leaves allows us to measure the rate or the speed of the reaction. In this case, it's an acid with a metal carbonate. Calcium carbonate, for example, with hydrochloric acid will produce carbon dioxide gas. The clue's in the name. If it's a carbonate, you're going to get carbon dioxide. If you've got a metal by itself, a metal and an acid always produces hydrogen all by itself. So just try and remember that. Metal by itself always produces hydrogen by itself. A carbonate is always going to produce carbon dioxide. Those are the only two gases that you would get if you're reacting an acid with any kind of metal or metal compound. Right, so if the mass was to decrease, we can actually talk about the gas that is formed, and make sure you do state the name of the gas in an answer. Why not? You might be able to work it out from an equation given, or you might be able to work it out from the reaction itself. My bets for 2017 is they might ask you to talk about a reaction in which a precipitate is made. I think they might give you pictures of equipment, just like I've got here. So you might not be able to read the screen, doesn't really matter. On the left hand side, you need to recognise that for once, a circle with a cross in the middle, it's not a proton, it's not a positive metal ion. In this case, and it's partly why they've labelled it, this is a circular piece of paper with a cross drawn onto it. That's going to allow us to put that underneath the conical flask and to see whether or not that cross disappears as the reaction happens if it's to go cloudy. So as soon as you see that equipment, you know it's a reaction where something is going to produce a solid, and that solid is always called a precipitate. Good use of keywords there, it's in the blue box underneath. So there's my apparatus. I might be asked to design an investigation, I think they might ask you to look at the rate of reaction based on changing temperature. So you've got two measuring cylinders on the right and the conical flask in the middle. Looks like an upside down cone. That's why it's called conical. We just say conical. Again, if you're asked about these reactions, state the product that's formed. State that you know the product's going to be a solid and it's going to make the solution go cloudy. That's the word we use. It's not going to mess up the solution. It's not going to make it go woolly or anything else, just cloudy. That's the word we need to use. Right, if they asked you this, if they gave you those pieces of apparatus and they said, write an investigation or write a method, describe how you'd use this equipment to investigate the effect of temperature on the rate of reaction, what are you going to do? Let's look at how you'd write that method using our 7 steps we saw in our previous video. Right, let's have a go. Okay, you're going to have lined paper. So we're imagining, I haven't, it's not going to be that tidy, but we'll go with it. You're imagining that your question was something along the lines of investigating a rate of reaction based on the equipment we just saw. So we had a circle with a cross on it, we had a conical flask, and we had 2 measuring cylinders. We're guessing that maybe they might ask us to talk about temperature change. If I could spell the word temperature today, that would help. Temperature. Okay, investigating the effect of temperature on the rate of reaction. So, what do we say we have to do first? Measure. There's something we're going to have to measure. So first of all, we're going to need to measure how fast this reaction is going to go. We need a time, and we need something that's going to happen in that time. We've already talked about this solution going cloudy. So the first thing I'm going to write down is I'm going to measure the time taken for the solution to go cloudy. I need to make sure I know when to stop and start my stopwatch, so I'm just going to write it down. Start the stopwatch as soon as the chemicals are combined. Now I've said chemicals. In an exam question, you'd be given the name of the chemicals, so use them. So write down, it might be sodium thiosulfate, that's the one you've seen in lessons before, that makes that slightly yellowy, creamy coloured solution. So if it is sodium thiosulfate, with, for example, hydrochloric acid, then write that down. So start the stopwatch as soon as the chemicals are combined. As soon as the sodium thiosulfate is added to the hydrochloric acid. It might ask us to say how we're going to use this apparatus. Measure. Remember, we've got to talk about exactly what we're going to do, and we've got to keep our variables the same. So measure the same volumes and concentrations. It's only the temperature we're going to change in this case. The same volumes and concentrations of each chemical using, remember they gave us measuring cylinders, using a measuring cylinder. Now, because I've revised really well, I know that in order to be accurate, you need to use a measuring cylinder with the smallest resolution possible. Might as well include it, it's going to take me a few seconds to write it. So, use a measuring cylinder with a resolution size closest to the volume you want. And I might as well put an example to explain what I mean. E.g., use a 10 centimetre cubed measuring cylinder for 10 centimetre cubed volume. Right, we've done the measurements. We've said we're going to measure how long it takes for the solution to go cloudy. We've said when we're going to stop and start our stopwatch. We've talked about what's actually going to happen, because we've said about it going cloudy, but not exactly how we're going to know. When has it gone cloudy enough? How are you going to know that reaction is finished? So stop. In fact, I'm not even going to go there. Let's talk about this piece of equipment here. So place the paper with the cross under the conical flask before you add the chemicals. So measure the same volumes and concentrations of each chemical using a measuring cylinder. Use a measuring cylinder with a resolution size closest to the volume you want. E.g., use a 10 centimetre cube measuring cylinder for 10 centimetre cubes of volume. Remember, I've not used the word amount anywhere. Place the paper with a cross underneath the conical flask before you add the chemicals. Doesn't matter which order you add the chemicals in, as long as you don't add them together until you're ready to start your stopwatch. But they've got to be at different temperatures, so how are we going to do that? So to change the temperature, they might even have shown you a water bath. Water bath is basically just like a big plastic crate with a heater inside it, which gets the water to an accurate temperature, and it stays at that temperature the whole time. To change the temperature, heat or cool the solutions, depending on what temperature you need, separately. So remember, as soon as you mix them, they're going to react, so you need to get them to the right temperature before they react. So separately, okay, cool the solutions separately using a water bath, correct apparatus, using a water bath, until they reach the temperature you need. Okay, so let's just check back what we've done. Measure the time taken for the solution to go cloudy. How are we going to know when it's gone cloudy enough? We haven't said that yet. We need to come back to that in a moment. Start the stopwatch as soon as the chemicals are combined, as soon as the sodium thiosulfate is added to the hydrochloric acid. Measure these same volumes and concentrations of each chemical using a measuring cylinder. Use a measuring cylinder with a resolution or size closest to the volume you want. For example, using that 10 centimetre cube measuring cylinder for the 10 centimetre cubed volume. Place the paper with a cross under the conical flask before you add the chemicals. To change the temperature, heat or cool the solution separately using a water bath until they reach the temperature you need. So what are we going to do to finish it off? We need to say how we're going to know it's gone cloudy. So as soon as the reaction starts, in fact, let's make it easier for ourselves. I'm writing this from scratch off the top of my head. You'll be doing the same in an exam, so you might need to do a little bit of planning. You can put lines through stuff. You can even ask for extra bits of lined paper, but try and keep this question to under 10 minutes of your hour. Right, so let's go for our step-by-step method. So add the acid to the conical flask. You've already said you're going to put the cross underneath. Start the stopwatch as soon as you add the sodium thiosulfate. Look from directly above at the cross. Stop the stopwatch as soon as the cross can no longer be seen. Okay, right. The time this takes is our dependent variable. Right, so what do we say we're going to do? All our measurements are there. A step-by-step method is there. We said how we're going to change the temperature. We need to make sure we state that we repeat the investigation using solutions at different temperatures. They might tell you what temperatures they want you to use. Or again, why not just add some in? E.g. 10, 20, 30, 40, 50 degrees C. Range of 5 is good. And why not finish off by saying, repeat the investigation 3 times and calculate an average. As I said earlier, if they've asked you to also write a risk assessment, you would then need to talk about the risks of the individual chemicals, knowing that acids are corrosive. The hazard there being that obviously they might end up getting in your eyes, causing you burns, so you need to make sure you've worn goggles. They're going to be looking for fairly straightforward risk assessment things. They're not going to be asking you anything tricky, but knowing words like corrosive, irritant, and using those in relation to acids and alkalis will gain you extra marks. Obviously, if it's a use of a Bunsen burner, you go through your usual stuff, making sure you tie your hair back, making sure you get loose clothing out of the way, and obviously always include that you're going to wear goggles, because let's face it, we normally do. Right, that was how you'd write a method for the effect of temperature on the rate of a reaction, using a reaction where you're going to get a precipitate or the solution's going to go cloudy. Get practice in. Remember, we had 7 things to include. Measurements, measuring a time, measuring something that's going to change in the reaction, talking about exact details. When are we going to stop and start our stopwatch? How are we going to know if the reaction's actually finished? Talking about specific names of apparatus, conical flasks, measuring cylinders, pipettes, and so on. Making sure we talk about what we're going to keep the same. Avoiding using the word amount, instead talking about concentrations, volumes, and masses. This experiment didn't involve anything other than liquids, so I don't need to mention the word mass, because mass is to do with solids. And then finally, have we got a variable we need to change? Make sure we've stated that we're going to change it. And finally, repeat the experiment times 3 and make sure you calculate an average. Good luck, practice, come up with ideas yourself about what your questions might be. And if you come up with anything you're stuck on, please come and see us and ask for more advice. Hope you've enjoyed the video. Keep watching them. Happy revising.